Hello everybody and welcome to yet another math video. In this video I will be going over how to work with linear inequalities in two variables. First I'm going to go over some vocabulary and just some basic ideas that you'll need in order to be successful with linear inequalities in two variables. I will go over the process for graphing linear inequalities with two variables, and then I will do some applications at the end. Let's get it. Vocabulary and basics. Since there are two variables, these types of inequalities will be graphed on an xy coordinate plane. So this looks a lot like graphing linear functions, where you can have linear functions that are slanted one way, sloped one way or another, either positively or negatively, or they could be horizontal lines with slope 0 or vertical lines with undefined slope. You may notice that these boundary lines come in two different types. We have dashed boundary lines and solid boundary lines. So a dashed boundary line is what you'll get if you have a greater than or a less than sign. And a solid boundary line is what you'll get if you have a less than equal to or a greater than or equal to. Now you may notice that one of the other things that is brand new about this is that there is some shading going on here. The boundary lines basically break our coordinate plane into two areas, and we have to figure out which area to shade. It's as simple as picking a test point, and I will go over that in a minute, but the shaded area is what we would call a solution set. And the solution set is any ordered pair in the shaded area or on a solid line. So while the point here, 4, 0, is on the line, this line is not solid, and we could not include 4, 0 in our solution set. Here's a quick check of that. So if x is 4 for this point here, if x is 4 and y is 0, and I substitute those values into the inequality that is given here, the left side becomes 12, the right side is still 12, and you get 12 is greater than 12, which is false. So we cannot include any points on the line here. But for a vertical line here, we can include anything on this line. If we pick a point right here, let's pick this point right here. That is 3, -4. And I check it only in this inequality. The x value here is 3. If I substitute 3 in for x, 3 is less than or equal to 3. Yes, that's very true. So we can include any point that's on the line or any point in the shaded area. On this slide, we'll be answering the question, is the ordered pair in the solution set? So I have two ordered pairs here, 0, 5 and -2, -7, and I'm asking, are these ordered pairs in the solution set for this particular inequality? It's very easy to check. What we can do is pick the point 0, 5, the ordered pair 0, 5, and we can substitute it in for x and for y. So 2 times 0 plus 2 times 5 is bigger than or equal to 8, and we're just trying to see if this is true or false. So 0 times 2 is 0, 2 times 5 is 10, so I get 10 is bigger than 8, and that is true. So this one is in the solution set. Whereas if I pick -2 and -7 and substitute those in for x and y here, -7, multiply both by 2, add them together. Let's see, I get -4 for the first multiplication and -14 for the second multiplication. When you combine those together, it's -18 is greater than or equal to 8, and that is definitely false. So this ordered pair is not in the solution set. But there could probably be an easier way to see that. If we look at the graph of this two variable inequality on a coordinate plane, you can see that the ordered pair 0, 5 corresponds to this point right there. And that, yes, it is in fact in the shaded region. And the ordered pair -2, -7 corresponds to this point out here. And this point is not in the shaded region, which means it's not a solution for the inequality. Okay, so how do you go through and graph linear inequalities so that you too can find solution sets very easily? The process for graphing linear inequalities involves two steps. One, you have to graph the boundary line, and you'll use a dashed line if the inequality symbol is less than or greater than, and you'll use a solid line if the inequality symbol is less than or equal to or greater than or equal to. The second step is you will choose a test point that isn't on the line and actually test the inequality. If the inequality is true, then you shade on the test point side. If the inequality is false, then you shade on the other side. As a quick example, there's a prompt down here that says to graph this inequality, this two variable inequality. Now we can use some ideas that we've talked about in the past that since this inequality has two variables in it, we know it will cross both the x and the y-axis. We can also use the slope and the y-intercept to graph this inequality. But before I even do that, I want to notice what kind of inequality sign I have. This is a less than or equal to, which means I will be graphing a solid line here. And you definitely want to know what type of line you're going to draw in here, whether it will be dashed or solid before you actually do it. So there will be a solid line here. I know for sure that this graph has a y-intercept of -4, so I would put a line down here, or sorry, a point down here at y equals -4, the y-intercept. And then the slope is telling me to rise 5 and run to the right 2. So I will go up 5 and right 2. And I will go up 5 and right 2. And I will go, I guess I'm out of room that way. So to go the other way, I will go down 5 and left 2, and that point still looks like it's on the line. So there is the line that is graphed. That actually is the line y equals 5/2x minus 4. And now we have to pick the test point. So you can pick a test point anywhere. It doesn't matter, as long as it's not on the line. So for example, I'm going to pick 0, 0, because 0, 0 generally is the easiest point to plug into an equation. So off to the right here now, I'm going to substitute in 0 for y, which will look something like this. And it'll be less than or equal to 5/2 times x minus 4, but 0 will be substituted in for x as well. And all we're doing is we're trying to see if this is true or false. So on the left side, I end up with 0, and on the right side, I end up with -4. So what this is telling me is that 0 is less than or equal to -4, which is false. So what happens? We picked a point that was on the false side. So we don't want to shade over here because everything over here will make the inequality false. What we would rather do instead is shade everything over here because this is what will make the inequality true. So you can pick any point in that red shaded area, find the x and y coordinates, substitute it into the original inequality, and it will be true every single time. A couple more graphing examples here. Graphing the first example, 3x minus 5y is less than or equal to 30 would be better if we had it solved for y. So the first step that we will need to do here is subtract 3x from both sides. So this will be negative 5y is less than or equal to negative 3x, and that is going to be plus 30. The second step here in isolating for y would be to divide by negative 5. And this should set bells and whistles off in your head, especially since we are working with an inequality. This will reverse the direction of the inequality sign. Anytime you multiply or divide by a negative, here's your reminder. Anytime you multiply or divide by a negative number in an inequality, the inequality sign changes directions. So really, we will be graphing this thing right here, 3 over 5x minus 6. So I can plot this here. This will be minus 6. This will be up 3, right 5, right there. Up 3, right 5, which will be right there about. Down 3, left 5, which will be right there. Fantastic. And way back here at the beginning, and I didn't do it at the beginning, but I'm going to do it before I put my line on this graph, I could have looked here. It doesn't matter that the inequality sign changed directions. This was always going to be a solid line right from the start. So I'm going to freehand this. There it is. I freehand a line. It's a solid line. There's the boundary line. Now, which side of this line do we shade? Do we shade the top part or above the line, or do we shade the bottom part, or we would say below the line? Well, again, the easiest way to do this is to pick a test point. So to pick a test point, I see 0, 0 is available. So I'm going to pick 0, 0 as my test point. So I'm going to substitute 0 in for y and 0 in for x, and then I will have an inequality that looks like this. If I simplify everything down on the right side, I will have 0 is greater than or equal to negative 6, which is true. So then what I will do is absolutely shade on the same side as that point that I picked. Since I picked over here, I will shade in, but I will not cross the boundary line. That's what it's a boundary. You cannot cross it. So here's where I'm shading. And so any ordered pair in that shaded area, and in addition to that, on this line, will make this inequality true. Now for this next example, we're going to take the time to graph two inequalities on the same coordinate plane. And I made them relatively simple. I wanted these to not scare anybody. So I'm going to graph the first one here. X is greater than negative 5 in red. And again, this inequality only has one variable in it. Since there's only one variable, all we have to do is find this number on this axis, and then just make sure it will never cross the other axis. So there's negative 5 on the x-axis. This line can only cross the x-axis, which means it has to be parallel to the y-axis. And very quickly, before I graph this here, this will be a dashed line. So I'm going to have to dash this in. There we go. So dashing in that line. And again, I am just going to pick a test point to figure out where I should shade. And I'm going to do something different this time because 0, 0 is a good test point, but I want you to see that you can really pick any point you want. So I'm going to pick, let's see, negative 8, negative 5, so way over here. So I have negative 8, negative 5. That's the ordered pair I'm using to test this inequality. So what I do is I substitute these numbers in where I can into the inequality. So if I have x is greater than negative 5, And I can only substitute the value -8 in for x because there are no y's. So I have -8 is greater than -5. Ooh boy, here come all the negative facts back at you. This is false. -8 is not greater than -5. So since this is false, I will shade on the other side of that line that we just drew in there. Let me get my highlighter. There we go. All right, so there's that. The next inequality I will be graphing in blue. So since there's only one variable, I have to find that number 7 on that axis y. So here it is here. And I know this will be a solid line. And this line can only cross the y-axis because that's the only variable that's in the inequality. So that means it cannot touch the x-axis, which means it has to be parallel to the x-axis, which means the line will look something like this. There we go. And I am going to choose this point here, 7, 1. So I'm going to just write down my inequality again like I did. So this is x is less than or equal to, or sorry, y is less than or equal to 7. And I picked the ordered pair here. This is 7, 1. And so I can substitute in the values that I know. So I only have a y in this equation, so I can only substitute a 1 in for the y is less than or equal to 7. That's true. And since that is true, I will shade on this side of the line where that test point was, because it's true. So I'm going to shade here. Ready? Oh, this shading is working out a lot better here. So where is the solution set now? The solution set is, I'm going to do this in a completely different color, is where these two shading areas overlap. So the solution set is here. It looks like it's in the lower left-hand corner. So I'm going to shade it in a little bit darker here. So this is the solution set that satisfies both inequalities at the same time. So if I pick any ordered pair in this darkened area here, the x value will be greater than -5 for that ordered pair, and the y value will be less than or equal to 7, right? We can pick points on this line, but not on this line. So for example, 7, 1, the x value is greater than -5, yep, and the y value is less than or equal to 7, yep, that's a good point. How about this point right here? 0, 7. If I take this point, 0, 7, 0 is the x value, that's greater than -5. Yeah, that works. 7 is less than or equal to 7, that's also true. So any point on this line works, but no points on this line will work. On this slide, I'm going to go over a couple graphing examples with non-negative restrictions. And non-negative restrictions won't make too much sense. Maybe you already know what they're there for, but it'll make more sense when we get into the applications. Some other things I need to talk about very quickly before I get into actually graphing anything are the scaling here. And I'm just doing this so that I can fit the graphs of these on the actual coordinate planes that I have. So when I jump 1 over here, that's really 10, 20, 30, 40, -10, -20, -30, so on. And over here in this example, it'll be by 100. So 100, 200, 300, 400, so on, so on. With that out of the way, these two inequalities that you can see in the first and the second example both represent what we call the non-negative restrictions. This is what they look like when they're graphed, and of course they're going to be solid lines because we have an equal to here and here. And all this does is it forces the x and y values to be in the first quadrant. So the x values have to be equal to 0 or positive, which means to the right of this red line, and simultaneously the y values have to be equal to 0 or positive, which would be above this blue line. So it forces everything to be either on the x or y axis or in the first quadrant. The only thing we have left to do now is to graph this inequality right here. And yes, on this side of the equation, that is negative 1,500. So the first thing that we will end up doing is adding 15x to both sides. So I'm going to write this down here below the scale. So this would be negative 50y is greater than 15x minus 1,500. Next, we would divide by a negative 50 to isolate the y. And we would end up with negative 3 over 10 plus 30. So moving back up here to graph this, oops, this is negative 3 over 10x. There we go. Now moving up here to graph this, we would start with the y-intercept here. I know it's going to go down 3 and right 10, which would be way over here. And I know that this will have to be a dashed graph. So something like this. So now we just have to figure out where will this shading happen. Well, we have a really good idea as to where the shading will be with these non-negative restrictions here. So we know it's either going to be shaded in the first quadrant above the dashed line or below the dashed line here in the triangle, if you will. So if you pick a test point, we have to pick a test point that is in the first quadrant and it cannot be on any of the lines. So let's say like 5, 5. I'm just going to pick this point, 5, 5. It's not on any of the lines and it's on the first quadrant. So I already know that this point works for the non-negative inequalities because the x-coordinate is not negative and the y-coordinate is not negative. Fantastic. Does it work for the only other inequality we have? Well, if we substitute 5 in for x and we substitute 5 in for y and you simplify all that down, you'll end up seeing that you'll get a false inequality, which means that we need to shade on the other side of this slanted line. And that means only this little area right here is what's going to be used for the solution set. So any ordered pair in that triangle, it could also be on this vertical part of the line or on this horizontal part of this line, but not on the diagonal line, will work. Now, we have this other example over here. I'm going to quickly solve this inequality for y, like so. And I want you to try graphing this and seeing where this takes you. Go ahead and pause the video and give it a shot. Here's what this particular solution looks like, solution set looks like. And there is a big difference between these two different solution sets. Let me extend that out there. So the solution set that you see on the left, the one that you just tried here, extends forever. So I extended this blue horizontal line and this red horizontal line. That goes on forever to forever upward and forever to the right, which means this green area just goes on forever upward and forever to the right. We call this unbounded area because it just keeps traveling up and to the right forever. Whereas this area over here is absolutely bounded because it's inside, it doesn't grow forever. It has an area that we would say is finite. You can calculate the area of this triangle, whereas this one just has an infinite area, and that's going to be very hard to calculate. Moving on to applications, I have here just a ton of phrases: less than, below, smaller than, that all mean less than in an inequality symbol. I've got a whole list here for each of these: for greater than, for less than or equal to, greater than or equal to. The first phrase here in each is what we say in math. So this sign is less than, this sign is greater than, this sign is less than or equal to, and this sign here is greater than or equal to. And all of those other ones are like real life English phrases that you should know that would translate over into these symbols mathematically, because English and math are two different languages. On to the translation. Now for some real translation. We start up here with the first example. Enrollment in finite math plus enrollment in calculus is less than 300 students. Now we are talking about linear inequalities that have two variables. And in this expression, or in this sentence, there are two variables. They're hidden in there. But we have enrollment in finite math. That's one variable because we don't know how many students are in the enrollment for finite math. And we have a second variable here, enrollment in calculus. So what I want to do is first define these variables. So I'm just going to call enrollment in finite math X and the enrollment in calculus Y. Now that we have our two variables, we can actually set up the inequality. So the inequality would be X plus, clearly, there's a plus there, Y is less than 300. So this is the inequality we would need for this statement. Moving on to the second example, this gets into the more real-worldy type of examples you'll see very soon when you do linear programming. So a dietitian is using 2 foods for patients. Each ounce of food M has 30 units of calcium, and each ounce of food N has 10 units of calcium. Minimum requirements for patients is 500 units of calcium. All right, how do we turn all of this English nonsense into a nice, compact math sentence? Well, the first thing, again, we need to go ahead and define our variables. We don't know how many ounces of food we're supposed to be giving our patients. So that will be our variable, aka our unknown. So each ounce of food M and each ounce of food N will be our 2 variables. So there are the definitions. Now, when we do this particular inequality, there is going to be some multiplication happening. We know that for every ounce of food M, we will have 30 units of calcium added to the total amount of calcium that a patient will receive. So it would make sense that if we use M and we use N, and we're trying to meet a minimum requirement of 500 units of calcium, that we would have to multiply the number of ounces of food M by 30 to figure out how much calcium would there be in total. Similarly, we would have to multiply the number of ounces of food N by 10 to get the number of ounces total, the amount of calcium total in food N. Now, minimum. If you rewind a little bit, you'll see that minimum means greater than or equal to. they have to get at least 500. That means 500 units of calcium or more. So here would be the inequality for this second scenario. For this slide, I will be going over an actual application problem. And our goal here is to set up a system of inequalities and then graph them. So the scenario is corn seeds cost $40 per acre and soybean seeds cost $32 per acre. How many acres should a farmer plant if she has $5,000? And that is a question. All right, so when we work with real world scenarios, real world applications, the non-negative inequalities will automatically be a part of this. And that is because the smallest number of seeds you can buy is 0, or the smallest number of seeds for an acre you can buy is 0. You can't buy negative 14 acres worth of seeds. It's impossible. So hopefully that gives you a little more indication as to why these non-negative constraints are included. What our goal is now is to figure out how can we take the rest of these numbers that we see and turn them into that third inequality we need in order to get a graph going. And before we even do that, we should probably define what these variables even mean. What is x, what is y? So in order to do that, let's say x and y are going to be defined in the following way. Let's see, what don't we know? We don't know how many acres, and more specifically, we don't know how many acres of corn, and we don't know how many acres of soybeans. So we should call x, I mean, you have a little freedom here, but let's say the number of acres of corn, you could call it soybeans, and then y would be the number of acres of soybeans. There we go. So now that we have defined our variables, we can then write out this last inequality. And I'm going to do better on the next example. You're supposed to define your variables first and then create your system of inequalities. So I will take better care on the next example about that. So we have our variables defined. We have our non-negative inequalities here, our non-negative constraints. What is the last constraint? Well, we know that it costs $40 per acre of corn, so it'll be, I guess, a price inequality. So we have a $40 per acre of corn plus $32 per acre of soybeans. And we know that the farmer has $5,000 to spend. Now, the inequality that goes in here is not even mentioned. We don't have any words. It says, how many acres should a farmer plant if she has $5,000? What you have to do is think about this for a few seconds. If she has $5,000, she cannot spend more than $5,000. She can spend up to $5,000, and she can also spend less. So she can spend less than $5,000 or all the way up to $5,000, which would be a less than or equal to. So now that we have our system of inequalities, again, I did this in sort of a backward order, we can solve this inequality for y to get this really nasty looking inequality here. And we can start graphing. We may have to approach graphing this a little bit differently than we've done before. So I'm going to make my units here. What will this be? 1 unit is 20. So I'm jumping by 20s here, like 20, 40, 60, 80, 100. 5 would be 100. And so on and so forth in all the directions. All right, so here are the non-negative constraints graphed here. I think what we need to do is graph this using an intercepts approach. So if I substitute 0 in for x, like you would here, if you substitute 0 in for x, you'll find that the y-intercept is 625 over 4, which is roughly, or more appropriately, exactly, 156.25. And since I'm jumping by 20s here, I know that'll be just below 8. Because 8 times 20 is 160. 156 is just below 160. Now we can do something similar for the x-intercept. We can take the y variable and substitute 0 in for y. And when we do that, the y-coordinate becomes 0. And if we solve for x, you'll get x being 125. And so 125 is about right here. So how did I do that again? Here it is down here. If you substitute 0 in for y, 32 times 0 is 0, effectively making that term useless. So we would have 40x equal to 5,000. The x-intercept would be 125. And I just realized that that is not the x-intercept where it should be. 125 is just past 120. So forget that point. All right, so right there. This will be a solid line. So I'm going to go ahead and draw my solid line in there. Then we just have to pick a point that is not on any of the lines and see if it will be the shaded area in the triangle or the shaded area on the other side of this slanted line. And you can pick this point right here, which would be, that would be 20, 20 because of the scaling. So if you substitute 20, 20 in here for x and y, multiply things, add them together, you'll end up getting a true statement, which means the inequality or the shaded region should be in here. Pretend it's perfect. In this last example, I am not even going to do the graphing. The graphing you will have plenty of time to get good at when you look into linear programming. All right, so with this one, we're just going to set up some inequalities, and right away, I know I'm going to have some variables. I'm not even reading the situation yet. I know I have to have two variables, x and y. Why do we pick x and y? Because we're going to be graphing them eventually, but not for this example. All right, so the same farmer wants to fertilize her corn crops. She can buy brand A fertilizer that has all this stuff and brand B fertilizer that has all this stuff. So how many pounds of each should be bought if she, first scenario, wants to have at least 120 pounds of nitrogen? Well, it looks like we're trying, or she's trying to buy different types of fertilizer. So I'm going to say X should be, we'll say pounds of, we can say brand A, and Y can be pounds of brand B. From there, we can start making our inequalities. We know our non-negative inequalities are here. X is greater than or equal to 0. Y is greater than or equal to 0. You cannot buy a negative number of pounds of fertilizer. And then for 1, we would have this extra inequality. Let's see, we're looking at nitrogen. So that means we would just be looking right here for A and B. So, percents. Percents do not work well in equations. Okay, so we'll have to use a decimal. So this would be 0.26 of x plus 0.16 times y. And we want 120 pounds. This is at least 120 pounds. So that would be a minimum. That would be your low end. You want 120 pounds of nitrogen or more. So here's your inequality for scenario 1. For scenario 2, I'm going to do it in a different color. For scenario 2, you would use the phosphate column. So 3% as a decimal would be 0.03 of brand A plus 0.08 of brand B. Would be less than or equal to 28 pounds, because at most she wants 28 pounds of phosphate. I hope very much that this video gives you a better understanding on how to graph linear inequalities with two variables, gave you a better understanding on being able to translate between English into math, and I wish you luck.